Yes, good evening to you all once again. I welcome you all to another beautiful presentation, which is our lecture number 18, in which we are going to see in continuation with our previous lecture, that is lecture number 17. In our previous lecture, we have seen the mechanical translational system. Mechanical translational system. This is what we have seen in our last lecture. So, in which again we have seen there are three basic important elements. What are those? So, that is the first element is mass element, that is mass, and it is denoted by the letter M. The second is the spring element, it is denoted by the letter K, and the third element is dash pot. It is called dash pot, nothing but denoted by B, and it is nothing but the friction coefficient, viscous friction coefficient. Normally, these are the three important elements that are associated with the mechanical translational system. And again, so in our last lecture, what we have seen, say for example, for any given physical or mechanical body, say for example, if it has some mass m, okay, then definitely it should have some displacement x, and then let us see that some f of t is applied on this particular body, and so we have seen, okay, this is what actually, so this is, say for example, this is the given body with mass m, f of t is nothing but the applied force, and x is the displacement, is it not? Then say for example, spring constant, so the spring is shown like this, that is connected to m, and then dash pot, normally it will be represented here in general, because this is, say for example, as reference, and here your B will be denoted by here. Okay, this is what x is the displacement, f of t is the applied force, m is the mass, this is the spring, this is the dash pot. Then in our previous lecture we have seen that so what is the basic relation between these three elements with respect to the displacement? Okay, so according to Newton's second law, we have seen that the applied force f of t, whenever you apply some force f of t on this particular body, these three elements, this is the mass element, spring element, and then your dash pot element, three elements will perform their respective opposing force with the applied force. Means that, so with respect to m, there is a force actually, that is called Fm. Okay, this Fm is nothing but the force offered by this mass element. F suffix m stands for m, this mass only. This is the force with respect to the mass. This is the opposing force by this mass element towards, opposite to the f of t, applied force. And then here with respect to the k, so here f suffix k will be offered. F suffix k is the opposing force offered by the spring element with respect to the applied force f of t. Means the opposing force, this is the applied force. For this applied force, this much of Fm is opposed by this mass element, and again for this applied force f of t, this much force means f suffix k, nothing but the force offered by the spring constant k, this much force is offered or opposed by the spring constant with respect to the applied force f of t. Similarly, considering to this dash pot element, so the force offered or opposed by this element is F suffix B. Let us call it a small fb. You can write capital FB also, nothing wrong in that. So this much force is offered by this dash part element with respect to the f of t. So means that these are the three basic elements associated with this mass element. And now the total, what are the total forces then? What are the total forces? F suffix m plus f suffix k plus f suffix b equal to 0. The sum of forces acting upon a body equal to 0. That is what your Newton's second law. The sum of the forces acting on that body. What? Sum of the forces. So force with respect to the mass element. The force F suffix k is nothing but the force with respect to the spring constant k. This is the force with respect to your dash part element. Okay. If you take the sum of these three forces, then this will be like this. That should equal to 0. That is the according to Newton's second law. And also we have seen what is Fm actually. So what Fm equal to? So what is Fm? What is Fk? What is Fb? This we have seen our last lecture also. And for your better understanding, for your just for your kind quick reference, I will explain you once again that what is Fm. Fm is equal to, we have seen, Fm is directly proportional to the acceleration. Okay, Fm is directly proportional to the acceleration. Then if you remove that proportionality, then you can write the constant m into d square x by dt square. This we have seen in the last presentation. Is it not? This is the force offered by the mass element, which is nothing but the opposing force with respect to the applied force f of t. So, however, this Fm is equal to F only. This F only. This is what we have seen in last lecture. This is the force opposed by the mass element. This is m into d square x by dt square. Similarly, what is the force offered by spring constant? That is F suffix k. So F suffix k is equal to the force offered by this spring element is directly proportional to the displacement x. Means F of k is proportional to x. If you remove that proportionality, then the constant will come. That constant is nothing but k into x basically. This F of k is almost equal to your F again. So this is what the second force. F of k is equal to this much. Similarly, what is the Fb? So this is equal to F suffix b. This is the force offered by the dash part element b, and the dash part element, here the force offered by this dash part element is directly proportional to the velocity. Velocity is nothing but dx by dt. So if you remove that proportionality, then you can have here b into dx by dt. Dx by dt. This is what your F. Is it not? This is what Fm equal to this much. What is Fm? Is nothing but this. Fm is equal to, you must remember, m into d square x by dt square. Wherever Fm comes into your problem, you must remember that Fm is equal to m into d square x by dt square. The mass element into d square x by dt square is nothing but the acceleration a. And wherever the spring constant k comes, then if you consider the force with respect to the spring constant k, then what is the force? Force is simply that constant multiplied by the displacement given, k into x. This constant multiplied by displacement x, that's all. That is the force offered by the spring constant. Similarly, the third one is the dash part element. So the force offered by the dash part element is equal to that constant into dx by dt. Dx by dt. So these are the three forces. Now you can sum all these forces, Fm plus Fk plus Fb. That is nothing but m into d square x by dt square plus kx plus b dx by dt equal to 0. These are the total forces acting on this particular body. Likewise, you have to remember. Now, so whenever this kind of problem is given, normally you will expect the mechanical translation problem in your competitive examinations like UPSC, IES examination. There is a descriptive part is there in UPSC, IES examination. In descriptive part, definitely you will be asked the question on this mechanical translational system, or otherwise sometimes you may ask from rotational system also, mechanical rotational system also. Okay, after finishing this particular topic, in next presentation or subsequent presentations we will see that also. Now, so whenever you will ask the question on this particular mechanical translation, there is normally two questions you will be asked. The first question or point A is write down the differential equation associated with that given mechanical system. Write down the differential equation for that given mechanical system. That is the first point. And coming to the second is find out the transfer function of the given mechanical system. These are the two possibilities you will be expected to solve for the given problem. The first point is write down the differential equation, and the second is find out the transfer function for the given. That you must keep in your brain, and I will explain you what is the differential equation, how the differential equation will be noted down for the given mechanical problem for this given system, as well as how the transfer function is obtained. Okay, before going to that, just I will little bit give you some information to you. Say for example, just you observe these forces here. Fm is equal to m into d square x by dt square. Fk is equal to k into x. Fb is equal to b into dx by dt. What you are observing here? So here, if you see m into d square x by dt square, some derivative portion you can see here. K into x, okay, there is no derivative in this, directly k into x, constant into displacement. If you see the dash part, b into dx by dt, it is involving one derivative part is there, this is another second derivative otherwise. If you sum all these forces, you will be having one equation, means m into d square x by dt square plus b into dx by dt plus k into x equal to 0. That is what one equation basically. That equation is called the differential equation. That equation itself is called the differential equation. Okay, that I can explain you while solving one example. So after completion of this introduction, I will give you one example. I will explain you an example in which I will explain how the differential equation can be written, noted, and then after that how the transfer function will be obtained for that problem. Is it not? So now these are basically the differential equation involves these parameters only. Next, coming to the transfer function, coming to how to find out the transfer function. Okay, so what is the transfer function first? What is a transfer function? Already since from the beginning of our lectures, we are continuously speaking about the transfer function. The transfer function is nothing but it is the Laplace transformation of output by Laplace transformation of input. Is it not? This is what we are continuously studying since beginning. So it is again Laplace transformation of what is our output for the mechanical system. Remember that, note down that. So in the given mechanical translational system, the displacement x is nothing but your x of t is nothing but your output. We have to consider L of x of t displacement as output, and the applied force F of t, okay, can be considered as input. That is F of t. This implies, so L of t of x of t. So if you apply the Laplace transformation for this x of t, this becomes x of s by. So if you apply the L of t Laplace transformation to the f of t, the small letter becomes the capital. That's all, f of s. Is it not? So Remember that Laplace transformation is also another excellent, beautiful transformation which is widely used in the control system in order to obtain the transfer functions. Okay, the beautiful, important character of the Laplace transformation is it's a very simple transformation which will be used, whereas it converts the time domain into the frequency domain basically. And however, this can be used for the continuous signals, but that we will see in later when we start lectures on signal system or digital signal processing. That also we are going to see after a short period. So right now, you at this moment, you remember that L of x of t, if you apply the Laplace transformation to the x of t, the x of t is here, t is nothing but the time domain. Means it is a time, x in terms of time. So the parameter x is in terms of t, the function. Otherwise, it is a function depending on time only. Similarly, it is the force basically, displacement depending on time, the force depends on time. That's what. So the time element is converted into s. S is nothing but frequency. So whereas if you apply the Laplace transformation, the small x becomes capital X and small f becomes capital Y, and t will be converted as s. Remember that t will be converted as s. That's all. This much only you remember right now, and later I will explain you in elaborate about the introduction of the Laplace transformation. There is a excellent, beautiful topic it is that I will definitely will cover whenever it requires as per the requirement of our subject concepts. Here, that much deeper sight is not required right now. As far as this subject is concerned, this much you just remember that. So if you apply the Laplace transformation for any signal, so it will be converted capital X and the time is converted as S. Similarly, so x of s by f of s, that is the transfer function for this given physical system. Therefore, t of f is equal to x of s by f of s. That's what we have to find out for the given problem. Now obviously, to find out the to find out the transfer function for the given mechanical system, first of all we need to draw the differential equation first. Is it not? So directly it's not possible to find out the transfer function directly. So to find out the transfer function for the given mechanical system, the first basic step is to write down the differential equation, and that differential equation consists of these parameters, these forces, these equations only, these elements. It will consist the differential equation. What it means? You have to what we have to do then? We have to apply the Laplace transformation for these parameters. We have to apply the Laplace transformation for these. So okay. Then I will explain you a little bit thing. For example, if you apply the Laplace transformation of these forces, what these will become? That I will see. I think you understood this. Next, so I will explain you that. For example, say this is the force offered by the mass element, and this implies, let us see that if I apply the Laplace transformation to this entire, means L of T of my F or Fm, whatever you can write, no problem. You can consider as F or Fm, both are same. That means if I apply the Laplace transformation to this F, this is the left hand side, this is the right hand side basically. L of T of F is equal to that means that L of T of your m into d square x by dt square. Is it not? Is it not? So what I am trying to explain you is that if you apply the Laplace transformation to this force balance equation of mass, this is called force balance equation. This equation is called force balance equation for mass element. This is called force balance equation for spring element. This is called force balance equation for the dash part element. Understood? Understood? So this is called force balance equation for mass element, force balance equation for spring constant. This is called force balance equation for the dash part element. So for this first one, means for this first force balance equation of mass element, if I apply the Laplace transformation, then L of T of F is equal to, so that means L of T of this total quantity we have to consider. So this means, this implies L of T of F, or you can say F of T also, no problem. F of t, then you can write f of t here. Then as I explained just now, after application of L of t, that is Laplace transformation, small f can be converted into capital F and t can be converted into s, f of s. After application of Laplace transformation, small f can be converted into capital F and t can be converted into s, f of s, after Laplace transformation. Then here if you apply this L of t of the quantity which is there in the bracket, where m is the constant, you just keep outside and you apply Laplace transformation to this part, d square x by dt square, d square x by dt square. M is constant, remember that. M is constant here. Then Laplace transformation of d square x by dt square. That's what it will happen, how it will change. Means Laplace transformation of d square x by dt square is equal to, remember that it is the second derivative, no? So basically, okay, it is the second derivative. So otherwise you simply can remember. So as we have second derivative, if you have first derivative, otherwise I will write this also for your understanding. Dx by dt is the first derivative, what it will, and L of t of x of t. So this equal to, what is L of t of x of t? What is L of t of dx of t? This is nothing but x of t in fact. This is L of t of d square x of t by dt square in general. Is it not? Say, for example, there are three elements are there which I am going to explain you that how they will become after application of the Laplace transformation. So L of t of x of t is nothing but your x of s. This is what your x of s directly. This is the first derivative. Remember that if you have 1 d by dt, then if you have 1 d by dt, and for the d by dt you are applying the Laplace transformation, then after the Laplace transformation 1 d by dt equivalent to 1s basically. 1s. S into this x of t becomes x of s. Is it not? So d by dt of x of t is nothing but now s into x of s. Okay? And now, so coming to this second derivative, here d square by dt square means that here if you have 1 d by dt, you will have 1 s. If you have d square by dt square means second derivative, then you will have s square into x of s. I think you are getting. Understood? D square by dt square means second derivative. Then after application of the Laplace transformation, this quantity will be converted like this, s square into x of s. If you have single, only s will come. If nothing is there, only directly x of s. Therefore, this implies, is it not? Now this implies what it will be? M. Is it not? For this, f of s is equal to, m is the constant. Then you now tell me L of t of d square x by dt square, how it becomes? D square, nothing but s square into x of s. Understood? So d square by dt square is nothing but s square and x of t is nothing but x of s. That is what f of s means. So after application of the Laplace transformation for this first force balance equation of mass element, you will be getting this as your answer. F of s is equal to m into m is constant, therefore it becomes s square into capital X of s. Clear? Then coming to the second one. So if you apply the Laplace transformation for the second equation, means L of t of f of t is equal to L of t of kx. Is it not? Here k is the constant and L of t of x. So nothing but this one, L of t of x of t. So what you will have here? K into x of s. K into x of s. I will write for you. So I will erase this, because these are the basic things we definitely should need in order to write the differential equation. Thereby we need to find out the Laplace transformation. That's why it is required to understand. This implies for the second equation I am applying the Laplace transformation of f of t. F of t. This is equal to Laplace transformation of kx. Is it not? Kx. So this implies your L of t of f of t becomes capital F of s. This implies L of t of k. K is nothing but constant. Take outside here. And now you can write L of t of x. Nothing but x of t. Okay. X is nothing but your x of t. Don't forget that. This equal to k into L of t of x of t. What it will? Capital X of s. Is it not? Therefore, your f of s is equal to, this is the equation. So, after application of the Laplace transformation for the second force balance equation for the spring constant, this becomes f of capital F of s, that is equal to k into x of s. Clear? This is the second equation after application of the Laplace transformation. Now, coming to the third one, means the third force balance equation, that is the dash pot element. If you apply the Laplace transformation for this, how it will become? Let us see the third one. Is it not? So, third one. For this, if I apply the Laplace transformation of f of t, this equal to Laplace transformation of, what is that? B into dx by dt. This implies L of t of f of t becomes your f of s. Clear? Then here b is the constant. Take outside your b. Then L of t of dx by dt. It is x is nothing but x of t. Always remember that. So d by dt is nothing but time. Dt is the time derivative of x of t. Always remember that. X is nothing but x of t. So okay, not necessarily to write on all the time. It automatically it means that x of t itself. So b into, so it is the first derivative. You have one derivative. Therefore, after the application of L of t means Laplace transformation, you will have one s and the small x converted into capital X of s. This is what the force balance equation after application of your Laplace transformation. Clear? So these are what, how the force balance equations in terms of time domain can be represented, can be converted into the frequency domain. So why I am explaining all these is that, so in order to obtain the transfer function for the given mechanical translate system, we need to apply the Laplace transformation for the differential equation which is associated for the given system. And for that differential equation, we have to apply the Laplace transformation, and then thereby you have to find out the ratio of transfer function which I just explained you, that x of s by f of s. Is it not? If you find out that ratio, your problem will be over. So with this introduction, just I want to finish this presentation, lecture number 18, and in subsequently we will see one important example of this mechanical translational system, and for that we note down, we can write the differential equation of that mechanical system, and thereby we will try to note down the transfer function of that system. Okay, I think you understood very well, and definitely I request you all to comment and you give your feedbacks, and then you definitely don't forget to share with your friends, so that every student and friend should be benefited. So that okay, so with this I conclude this presentation, and we will see the one example in the subsequent presentation. Okay, thank you one and all.